Okay, welcome to the first lecture in number theory. And this is going to be a little series I put together just on elementary number theory. So this should be accessible to high schoolers. My goal for this is to talk about the integers. So what are the integers? Well, what we use to denote the integers will be this boldface z, and as a set, this is equal to 0, plus or minus 1, plus or minus 2, and so on. But this is just a set, and really what the integers are is they're kind of we have what the elements are, but it's not just what the elements are, it's how they're related to one another. And so the integers form what are known as a ring. And the integers satisfy the so-called ring axioms. Namely, we have a set z along with two operations. So we have two operations that we're going to call plus and multiplication. And the ring axioms, they say the following. If x and y are in the ring R, so what we'll do is, let me move this over here. So it's a set R with an addition and multiplication. So if we have x, y, and R, and this symbol right here, this just means is an element of the set. So if you have two elements of your ring, then if you add them together, it's in your ring. So, and what we really mean by plus and times is plus, it's a function from r times r to r, where if you plug in x and y, this is just going to be x plus y. And similarly, you have that the multiplication is also a function from r cross r to r. That just means if you multiply two numbers, x and y, this is x times y, and sometimes we'll just write xy. So this is what it really means when we say plus and times. They're just functions from the Cartesian product to itself. So if you add the two, you stay in there. What else do we want our ring to satisfy? Let's say if we do x plus y, this is the same as y plus x, and this is for every x and y in R. So this upside down A just means for every. What else do we have? We have that there exists. So there exists, so this backwards E in logic, it means there exists an element that we call let's just call it E right now. Or we're going to call it 0 in R, such that 0 plus x equals x plus 0 is equal to x for every element x in the ring. What else? We have an associativity law. So for every x, y, z in the ring, so if we have 3 elements, if we do x plus y plus z, this is the same as x plus y plus z. So these are kind of, oh, we also have inverses. So this one is kind of minuses. So for every x in our ring R, there exists an element y in our ring R such that x plus y is y plus x is 0. And here we will say y is minus x. And if you know any algebra, abstract algebra, all this says, so 1 through 5, this says that R with plus is an abelian group, because these are exactly the axioms of an abelian group. But we also have multiplication, because we have this other function. So let's just say 6. For x and y in our ring, we have that x times y is also in the ring. 7, for x and y in the ring, x times y is equal to y times x. 8, there exists some element that we're going to call 1 in the ring, and we're going to say that 1 is not equal to 0, such that 1 times x is equal to x times 1 is equal to x, and this is for every x in the ring. 9, we have the associativity, so for every x, y, and z in our ring, x times y times z is equal to x times y times z. So these are all the ring axioms. Oh, I lied. So 6 through 7 kind of tells you how multiplication behaves. 1 through 5 is addition, but you can combine them in the distributive law. So if I have x, y, z in the ring, if I do x times y plus z, this is the same as saying x times y plus x times z. So you can distribute the x. And so, and similarly, if you have like x plus y times z, this is x times z plus y times z. So this distributive law tells us how addition and multiplication interact with one another. So that's kind of what the basics of the rings are. And just from these axioms, we can prove some things. So kind of maybe the first elementary proposition is 0 is the 0 in the ring is unique. So all we said is that there exists some element 0 in the ring such that 0 plus x is x plus 0 is x, but we don't know that that's necessarily unique. And the proof is, say we have 2 zeros. So say we have a 0 in our ring and some 0 prime in our ring, are both zeros. Then what we can do is, what is 0 plus 0 prime? Well, if we think of it, 0 prime acts as a 0, so 0 plus 0 prime has to be 0. But similarly, 0 acts as a 0, so 0 plus 0 prime is 0 prime. So 0 is equal to 0 prime, and it's unique. Similarly, we can have proposition that 1 in R is unique, and the proof is exactly the same. If we have 1 and 1 prime are both in R, are both act as 1, then, well, if we look at what is 1 times 1 prime, well, then viewing 1 prime as a unit, we get that this is 1, but you viewing 1 as the identity, you get it's 1 prime. So those are two kind of quick things. We also have the inverse is, when I say inverse here, I'm talking about here. So for part 5, or axiom statement 5, the negative is unique. That is, we know, so the proof of this is, say we have x in R, and we have y and y prime are in R, are such that x plus y is 0, and we also have x plus y prime is equal to 0. So our goal is to show, we want to show that y is equal to y prime. So what we'll do is, if we look at x plus y prime, what is this equal to? Well, if we view the parentheses as x plus y prime, we know x plus y is 0, so this is 0 plus y prime, which is just y prime. But we could also do the following. We can change the order, and this is the same as x plus y prime plus y. This uses associativity and commutativity. And now x plus y prime, we know that that's 0 plus y, so this is y. But these two things are equal, so since these two things over here are the same, these two things over here are the same. Namely, we have that y is equal to y prime. And from this, we can define subtraction. We could define subtraction in a ring is the addition of the additive inverse. And so, and we will denote this just by the minus sign. So if x plus y is equal to 0, then if we have some z, or maybe I'll say then subtraction by y, or by x, is the addition of y. So we've talked about the rings. So we kind of know what the integers are just from elementary school. And we know we can add them and multiply them. And now we can subtract them. But note, so maybe I'll put a note here. Note, you can't always divide. Since if we think about, like, what is 1 divided by 2? well, this is not in the integers. Just if we think of this as 1 plus or minus 1 and so on. So you don't necessarily have division. So this is kind of, the ring is kind of the basic building blocks of kind of algebraic systems. And we have these ring axioms, but you can come up with things that satisfy these axioms which are not the integers. Namely, so here's a quick example of a ring. This I'm going to call Z mod 2Z. And as a set, we're just going to think of this as 0 and 1. And since we only have 2 elements, I can write down addition and multiplication tables. So 0, 1, 0, 1. So if we have 2 elements, we know any ring has to have 2 elements because we're guaranteed by the axioms a 0 element and a 1 element that's not 0. And because of the addition, we know 0 plus anything is itself. And then what is 1 plus 1? Well, this has to be 0 here. And the reason being is, if this is a ring, there has to be an element that you can add 1 to get 0. And that element will be 1. And for multiplication, well, we know 1 times anything is itself, so 0, 1, 0. But what is 0 times 0? Well, I claim that is 0. And namely, so you can go and check that this satisfies all the axioms. So just stating that the integers is a ring, I mean, the integers are a ring, but not every ring is the integers. So, yeah. So, but what I said here, when I said what is 0 times 0, and I said 0, let's go ahead and do that. Let's say in a ring, 0 times x is equal to 0 for every element of the ring. So how can we do this? Well, what is 0 times x, right? Well, I can say this is equal to 0 plus 0 times x. Because what I'm doing is I am replacing this 0 here by 0 plus 0. And using the distribution property, this is 0 times x plus 0 times x. So now, what we can do is we can add, so we can add the multiplicative inverse of 0 times x. So basically we're subtracting 0 times x from both sides. So if you subtract 0 times x, this gives you 0 is equal to 0 times x. So we just showed that 0 times anything is 0, always. So, yeah, that is something we have done. So, let's think of what other properties the integers have that kind of lets them be different than the normal rings or from other rings. And one idea is the notion of an order. So an ordered ring is a ring with an order. And what an order is, it's going to be some subset of the ring. So we use P here to stand for positive. So we're going to think of P meaning positive. Such that P satisfies the three axioms, the following three axioms. If we have X and Y are in our order, then X plus Y is in P. So this is all this should be saying to you is if you have two positive numbers and you add them together, you're going to get another positive number. Similarly, if you have two positive numbers and you multiply them together, you should get a positive number. And the third axiom of an order is called the trichotomy axiom. I might have spelled that wrong, but basically it says if we have an element of our ring, then either X is positive, minus X is positive, or X is equal to 0. So you're either positive, negative, or 0. And so this is what an order is on a ring. But so if we go back to this example, so up here we can say Z mod 2Z has no order. Can we do this right now? Yes. So since 1 is either positive or negative, so 1 is equal to minus 1 here, right? Oh, I should say, when I say either here, I mean exactly one of the following is true. So if we have an element in the ring, then it's either positive or its additive inverse is positive or it's 0. So 1, since it's not 0, so either 1 or minus 1 has to be in P. But since 1, if 1 is in P, then minus 1 is not in P. But that can't happen because that would say 1 is not in P. And similarly, if 1 is not in P, then minus 1 is, or if minus 1 is in P, then 1 is not in P. But since they're the same, these statements can't happen. So we have this doesn't have an order on it. So, but what about the integers? So if we look at Z has an order, and the order is just the positive integers, 1, 2, 3, and so on. So what are some basic properties of the positive integers? So 1 is always in P. So if we have an ordered ring, 1 is always positive. So how can we prove this? I am going to move this down because there's something else we need to prove first. So -1 times x is equal to -x. And when I say -1 here, I mean the additive inverse of 1. So a proof of this is we know that the additive inverse is unique. So it suffices to show that -1 times x plus x, we can just show that this is equal to 0. So what we can do is we can write this as -1 times x plus 1 times x. Then we can factor this out using the distributive property. So we get -1 plus 1 times x. -1 plus 1 is 0, so that's 0 times x. And we showed that 0 times anything is 0. So namely, so we have -1 times anything is just its inverse. And then what I can do here, maybe I should move this down some more. So -1 times -1 is equal to 1. The proof is, well, -1 times -1 is equal to -1. So what is the unique element that when you add to -1 that gives you 0? It is 1. So yeah, this just follows pretty much directly from this up here. All right, so now we're ready to show that 1 is always a positive number. So how can we do this? So what we're going to do is we're going to do a proof by contradiction. So if we assume for sake of contradiction, 1 is not positive, then -1 is positive. Because if 1 is not positive, then -1 has to be positive, because 1 is not equal to 0. So then what is -1 times -1 is equal to 1 is in P a contradiction. And we're just using this fact here, that if you multiply two positives, it's positive. And this, we proved -1 times -1 is equal to 1. So this tells us 1 must be a positive number. So we have that the integers is an ordered ring. But there are rings that are ordered which are not the integers. For example, or probably the simplest example, is if you look at the rational numbers, which is quotients of integers. So it's everything of the form a divided by b, where a and b are integers and b is not equal to 0. This has an order, namely the positive rationals. So where a and b are both positive, per se. So we don't have the integers just yet. So there's something more that the integers must satisfy that we need to classify them. And that is going to be the well-ordered principal. Actually, I want to move this down some. So we talk about an order up here, but when we talk about an order, we can then define. So in an ordered ring, what does it mean for x to be less than y? And our definition of order is just having this set with the properties above. Well, if x is less than y, this just means that y minus x, well, y minus x would have to be greater than 0. So this would have to be in P. So here, this just means y minus x is in P union the set containing 0. And then you can similarly define greater than and greater than or equal to. So, yeah. Maybe another proposition. So I'm going to delete the well-ordered principal, and we'll get back to that. So on the topic of this order, if x is less than y, and x prime is less than y prime, then x plus x prime is less than y plus y prime. So how can we prove this? Well, if we look at x plus x prime, our hypothesis, this says y minus x and y prime minus x prime. These two are in P. And for this to be true, this just means y plus y prime minus x plus x prime has to be in P. But what is minus? So this is the same as saying y plus y prime plus -1 times x plus x prime, just using the definition of subtraction is adding minus. And then we can use the distributive property and this proposition up here to say this is just y plus y prime minus x prime. But this is y plus, or not y minus x plus y prime minus x prime. Both of these by assumption are in P. So since both of them are positive, their sum is also positive. So there we go. So yeah, that is one way to get positive numbers, or that just shows, yeah, if you add two bigger things, then the sum is greater than the smaller things, the sum of the smaller things. Let's see. What else could we prove? If x is less than y, and let's say z is positive, then I claim x times z is less than y times z. And how can we prove this? Well, by assumption, we know y minus x is positive, right? And since z is positive, this tells us that z times y minus x is positive. So namely, we have I'll write it as yz minus xz is positive, but this exactly says that xz is less than yz. So notice we had to have z positive here for this situation. Let's see. Okay, so now I think I want to talk about the well-ordered principle. So the well-ordered principle, it says any non-empty subset of P has a smallest element. And here, this is, we're talking about the integers here. So we're talking about the positive integers. And just thinking about what the positive integers are, 1, 2, 3, 4, 5, 6, 7, I mean, 1's the smallest out of that. So if 1's not in the set, then it's 2. But if 2's not in it, then it's 3. And so on. And since it's not empty, there has to be a smallest at some point. So that's kind of the intuition behind it. And these pretty much characterize what the integers are. We just show, so for example, or maybe this is a non-example, Q is not well ordered. Since if you consider the set 1, 1/2, 1/4, 1/8, and so on, so 1 over the powers of 2, these get closer and closer. This is an infinite decreasing sequence, and there's no smallest element. And so, yeah, we have the well ordering of the natural numbers. And this is kind of what separates the natural numbers. These are defining characteristics of what the natural numbers are. It's a ring, an ordered ring that satisfies the well ordering principle. Because, yeah, and maybe, can I do that? So let's do this. So here's a proposition. There is no integer between 0 and 1. So here's the proof. So we're going to do a proof by contradiction. Assume for sake of contradiction, there is some integer and it's between 0 and 1. Then, so x is clearly positive. Now let's consider x squared, right? So then I claim that x squared is smaller, or we're going to use the well ordering principle. So let x be the set of all integers that are between 0 and 1. By the well ordering principle, we have that there's a smallest. So maybe I'll just call y the smallest, or the least element. Now, let's consider y squared. I claim that y squared is less than y. So note, since y squared is positive, because y is positive, a positive times a positive is a positive. So this is because, so y squared is less than y. That just means if we look at y minus y squared, this is y times 1 minus y. This has to be positive, because we know y is positive by definition. And since y is smaller than 1, 1 minus y is also positive. So these are both positive, so their product is positive. But, so we have that y squared is an element, or y squared is an element of x, and y squared is less than y. But this contradicts y being the smallest. So this kind of rules out the scenario up here with the rationals where we just looked at all powers of 1/2 because they keep getting smaller. And since there's no integer between 0 and 1, this kind of tells us that we're like discrete steps, kind of like the number line. So it's like 0, 1, 2, 3, etc. So, let me think. So this is what the natural number, or what the integers are. But the question arises, is every well-ordered ring, so a ring that has an order that's a well order, is if I have a well-ordered ring, is it the integers? And that's kind of what I want to do. So maybe let's do a proposition. Any well-ordered ring is, I shouldn't say is the integers, I should say is isomorphic to the integers. And what do I mean by isomorphic? So if we go to, say, this example here, what would happen if I changed all the zeros to just A, right? And all the ones to B? Everything still looks the same. It's just we swap the symbol 0 for A and 1 for B. So it all looks exactly the same. And that's kind of the notion of what an isomorphism is. So let me just give you the definition. An isomorphism of rings is a let's call it, so it's going to be a bijective map, and I'm going to call it F from R to S. So R and S are my rings, where f of 0 is 0, f of 1 is 1, f of A plus B is f of A plus f of B, and f of A times B is f of A times f of B. So basically, it doesn't matter whether we perform the operation before taking the function or after. And so that is what an isomorphism of rings is. And so here's kind of the proof that any well-ordered ring is isomorphic to Z. So proof. Let R be a well-ordered ring. So there is a property of orders that I should probably prove first. So let me move this to the next page. Okay. So ordered rings are infinite. And here's kind of the proof of that. So assume for sake of contradiction, there is a finite ordered ring. We know 1 is positive, right? So what happens if we consider what is 1 plus 1? So we have 1 plus 1 is also positive, but so is 1 plus 1 plus 1. That's also positive. And 1 plus 1 plus 1 plus 1. This is also positive. And you keep going. Since you're finite, since the size of the ring is finite, what we get is at some point the element of the ring has to be the same. So we're going to have 1 plus 1 plus 1. If this is m times, this is equal to 1 plus 1 plus 1 n times. But now what we can do is we can just, and let's just say with m less than n. Now since we can just subtract this 1 plus 1 plus 1 m times, and we get that 0 is 1 plus 1 plus 1 n minus m times. But this implies that 0 is positive, a contradiction. And namely, this also shows that if we have an ordered ring, if we take 1 and we keep adding it to itself, we're never going to repeat. So kind of, if R is going to be a well-ordered ring, if we take the element 1 in R, and we just map, so we're going to take, we're going to send 0 has to map to 0, 1 has to map to 1, right? So what about if we look at 1 plus 1, right? And this is going to be in the ring R. Then I claim there is no integer between 1 and 2. Because if there were, we could just shift things down to get an integer between 0 and 1. So all you do is you send 0 to 0, 1 to 1, and then you just have to extend the homomorphism to the integers in the natural way. If you send f of 0 is 0, f of 1 is 1, and you extend f to be a homomorphism. So a homomorphism, it's the exact same thing, but we no longer require it to be bijective. Then I claim this is an isomorphism. So, oh, and I guess I should also say f of -1 is equal to -1. So, kind of, why is this an isomorphism? Well, we know 0 maps to 0, 1 maps to 1, -1 maps to -1. Here's a question. Does this define where everything goes? So, when I say extend f, all I mean is we know where 0, 1, and -1 go. So if I have, so I require that f of 1 plus 1 to equal f of 1 plus f of 1, which is equal to 1 plus 1, which is 2. And similarly, f of -1 minus 1 is f of -1 plus f of -1, which is -2. So that's what I mean when I say to let f be a homomorphism, or to extend this rule to a homomorphism. So this function here, it's clearly going to be, so the extension's clearly onto, because if we have, so it's clearly onto, since if we take n in the integers, say it's positive, if it's negative, you can do the same thing, then f of 1 plus 1 plus 1 n times is equal to n. Likewise, how do we know it's injective, or one-to-one? So, say that we have f of a is equal to f of b, right? Now I want to show a is equal to b. Then, f of a minus f of b, well, this is 0, but it's also f of a minus b is 0. So it suffices to show that what we'll call the kernel of f is 0, where this is everything in R that gets mapped to 0. And it's clear that 0 gets mapped to 0, but what's not clear is how do we know that there's going to be some other elements that does not get mapped to 0? And basically what it boils down to is we talked about extending this homomorphism f, and the question is, does f extend to all of R? And that is kind of the question. So say we have some element. Okay, so I think this all depends on something a little bit different. So I defined the ring axioms up here, and we can't just, this won't work, because what we could do is we can take z squared, right? And this looks like this. Oh no, but z squared is not, okay, never mind. Or could I take z squared? So what I might do is take, say, all the lattice points, right? Oh, but that's not close. Okay, never mind. I think we should be good. So I was thinking that maybe we needed to define this for domains, which have the property that if x times y is 0, then either x or is 0 or y is 0. But let's not do that. So say that we have some elements, right? X and R that f does not extend to. And let's just say x is positive, so x is greater than 0. Well, what if we take x to be the set of all elements of R such that f does not extend to x and x is greater than 0. So we'll take this set and then we'll use the well ordering principle. And let's say y in x is the smallest. Well, what do we know? We know y is positive, right? And what this tells us is, so this will tell us, we know y squared is less than y. No, that's not true. So take the smallest element that does not extend. So we know that y is strictly greater than 1. Because there is no integer between 0 and 1. Note for no integer between 0 and 1, that fact, so this, all we used is the well ordering principle. So if we have a well ordered ring, there is no element of the ring between 0 and 1. So y has to be greater than 1 because we know f extends 1 because f is defined at 1. And so we have, and there's no integer between 0 and 1. So we have 1 is less than y. So this implies that y minus 1 is positive, right? But what does it mean that y minus 1 is or y minus 1 is not so y minus 1 is positive, but it's also, y minus 1 is not in x, because y minus 1 is less than y. So this implies that f extends to y minus 1. That is, so we'll have y minus 1 is like a 1 plus 1 plus a bunch of 1s. But what does this tell us? This tells us, but then y is just equal to 1 plus 1 plus 1 plus a bunch of 1s. Namely, one more 1 than this. But this would imply that f extends to y. A contradiction. So we know that f extends to all the positive numbers. And similarly, f will extend to all the negative numbers, just kind of by symmetry, you can mirror this argument. And so we have that so f extends to all of R. And namely, we showed that every element of R, every positive element of the form 1 plus 1 plus a bunch of 1s, and every element of minus R is like, or every negative element is just -1, -1, -1, -1. And namely, none of those are in the kernel, so we're injective. And so we just showed that a well-ordered ring is isomorphic to the integers. And yeah, so this is pretty much, I mean, at a very basic level, if someone asks you what the integers are, this is what they are, and what define them. So I don't want to say I'll say a defining characteristic of the integers is that it is a well-ordered ring. And since it's a defining characteristic, any well-ordered ring is the integers. And when I say you can have well-ordered rings on other things as well, but this respects the addition and multiplication structure. So that's what it is. So yeah.